Hey, what's up, guys? This is Cheng here. So this time, LeetCode number 1977, number of ways to separate numbers. Okay, so this one is another very hard problem. Okay, but idea of the problem is not that hard. The difficulty for this problem is how to improve the performance or how to reduce the time complexity. Okay, so the description is also not that long. Okay, so you have like positive integers in the string mode, in the string format, right? But and you want to separate it. You want to separate those the strings, right, into several different numbers. Uh, while those separated numbers are non-decreasing in non-decreasing order. Okay, and no integer had leading zeros, right? And you need to return the number of possible lists of integers that you can split, right? From this number. And since the answer may be large, return the module, returned by the modular, right? So I think, you know, every time when you see this kind of do a modular by this one, the total ways will be huge, right? That's why you need to do a modular here, right? In that case, you will always need to use the dynamic programming. Basically, you cannot do a brute force search, right? Because the number will be too big, right? And if you do a brute force search, it will definitely TLE. That's why every time you see this one, it's always a signal to ask you to use dynamic programming, right? And for example, we have 237, right? So this one, we only have two answers because there are only two ways to split it, right? So either like split it to here, right? Split it to here, where we have 3 and 27, right? Or we can just split uh, here, right? Basically, split it here, where we have 3 to 7. We cannot split it here like this, right? This is wrong because this will give us like a decreasing sequence. Okay. And example 2 here, right? There's like 094. Uh, in this case, you know what? We have 0, and the reason being is that someone said, okay, can we do like 9 and sorry 0 and 94, right? So this could be a valid answer, right? But there's another like constraints here. So all the numbers, right, has to be positive. So which means 0 is not an option, right? So basically, whenever we see a 0 to start, we know it's not a valid answer in this scenario, right? So obviously this one is also a 0, right? And then here we have this one is 101. Okay, and the constraint is like this. So basically 3,500, right? To solve this problem, let's start with the very basic, right? And then we can improve our algorithm one step by step so that we can pass all the test cases. Okay. So first, the idea of doing this in dynamic programming shouldn't be that hard because I think this one is kind of similar to another basic dynamic programming. It's called Decode Ways, right? So basically, in Decode Ways, we just simply based on current one, we just get the based on the current state, we can get the current state from the previous state, right? In this case, what is the current state, right? So let's say we have this kind of, let me do this in the blackboard here, okay? Right, so in this case, let's say we have this number, right? And this is I, right? So let's say ending with is I, right? So with this string here, right? So a common state is that the first state will be I, right? I means that okay, so we current the current string ending as I, right? And then what's the second one, right? Because we know the current state ending with I, and we want to know all the possible ways that we can get to the current possible ways that we can we can get, right, by ending with the current state, by ending with the I here, right? But then we need what? We need the second state here, which will be the length. Okay. So that basically the length is telling us the state that we're ending with I, and the last number has length of this L. For example, let's say we have this. This is L, right? So L in this case is 4, right? So it means that okay, so here that's the last number, right? That's the last number we're currently looking at, okay? And if we define the DP in this way, right? So in the end, so what's going to be the final answer if we define it in this way? Basically, it's going to be the sum, right? Going to be the sum of DP, right? DP what? DP n minus 1, right? N minus 1 means that okay, we're ending with the last one, and this is going to be the length of k, right? So where k is equal to from 1 to n, right? Because since we're getting all the ways that we want to get all the ways that we can decode, right? This current string, the length could be the last integer could be either this one or this one, this one. That's why we have to accumulate all the length, right, from this DP. So that's gonna be the initial DP definition, right? And if we have this DP I and L, right? So how can we get the state transition function, right? So assuming we have this L equals to 4, right? And how can we get this the ways for this state? And naturally we will just simply look at the previous letters, right? So the ways we can get to the current state is that the previous number is smaller than the current one, right? So in this case, if so the previous number has to end here, because remember we're splitting this array, right? So there's couldn't be any skip here, right? Gap here. That's why obviously we have L equals to 4, and this number is okay because the length is smaller than the current one, and it's obviously smaller than the current one, right? And this one is also okay, right? And the 3 is also okay because all these 3 numbers they will definitely smaller than this one, right? But here, right, this one we have to check. It's not guaranteed this one will be greater, will be smaller than this one. We have to check these two numbers basically to compare them, right? So that's why we have this one gonna be a sum of dp. Let's say we have I, and let's say there based on this L, we can easily get the J here, right? So J is the start of this. The last number, and I is the end of this last number, right? So that's why we have this one. It's going to be what? It's going to be a dp of j minus 1, right? J minus 1 and then the k, right? Where k is equal from 1 to L, right? Or L minus 1, right? So that's the state transition function. Because so this dpj minus 1, because dpj minus 1 means that we're getting the total ways that ending here, right? Ending here. That's the previous number's last digits, right? And then the length. How about the length? Like I said, with the length we need to loop through from 1 to 3 for sure, and basically to 1 to L minus 1. But for L, we have to check if this L, when it is L, right? We need to check if this previous number is smaller than this one. That's why I put like option sign here, right? So that's basically the first version of it, right? So we simply do this, and since we have two DP state, it's going to be a nested for loop, right? So basically the outer for loop will be looping through each the ending point, right? And the inner loop will be looping through all the length. Okay. So let's try to implement the first version, right? And then we can improve on top of it. How about that? And let's do it. Let me see. We have, yeah, so what do we have? We need n here, obviously, right? It's going to be a length of num, right? And then we have dp, right? So dp is going to be, I'll do this n plus 1 because for this in range of n plus 1. So the reason I do n plus 1 is because actually the first one, n will be enough because we're only looping through from 0 to n minus 1, right? But for the inner one, since the inner one, so it's going to be, okay, so let me try the dp I and l, right? Because the total ways to split the string, right? The string with last number at I and the last ending, okay? And the length of last number is L, right? So that's the definition of our DP, right? And since that's what, so for the inner loop, right? For the inner DP, since we're talking about the length, right? So that's why the last one gonna be n, right? The total length gonna be n. That's why I do n plus 1 here. Okay, and then for the DP, right? So for outer loop, it's gonna be n of n, right? Oh, by the way, we're using a bottom up DP approach in it for this time. I think a top down will also work, but I think bottom up for this one is cleaner. Okay, so the outer loop is that we simply just loop through the ending point one by one, right? And the inner loop will be like this. L is going to be in the range of 1 to I plus 2. Okay, I know this one is a little bit weird because for the inner loop I need to loop through the length, right, from the current state. Let's say until from 1 to the whole length. Since I is 0 based, but the but the length is 1 based, right? That's why I have to do a I plus 1 to make sure the length can reach I plus 1. Can reach I plus 1 because let's say we are at like here, right? So the I is like 0, 1, 2, 3, 4. So when I is equal to 4, the biggest length is what? Is 5, right? Because because I is 0 base, L's length is 1 base. That's why I have to do a 1 to I plus 2 to make sure we have the last one is I plus 1, right? Okay. Okay, and then okay, so we have this I, we have L, right? And then so the next thing is that let's get J, right? J is going to be a L minus L plus 1. So J equal to the start of the last number, okay? So when J is equal to 3, right? We have I, and then we have the J is pointing to here, right? I'm simply using this J for the future use. Create this J, and then let's implement that state transition function here first, and then we'll handle this no leading zero case. So let's see. I'm going to define like a max L2 in this case, right? So X. So this max L2 is is the biggest that we can loop through for the previous ladder, right? For example, we have I here, and L is equal to 4, right? In this case, it's going to be this is L, right? So the previous ladder, basically depending on what is the biggest length of that we have left for the previous string, and also if this one is smaller than this one, the max L2 will be different, right? Because we simply cannot use L minus 1 as a base, because let's say when the L is here, when the L is here, see, we only have two numbers left, right, for us to iterate. That's why we cannot simply use L minus 1 as a base. So there are a bunch of ways. Let me just do this. And this max L2 will be basically be the times the number of loops, the checks we need to do for the previous numbers, right? Depending on those kind of factors. So if the j is smaller than L, right? So what is the j here? So j is here, this one, right? And what's the value of j? And even okay, so first it's the start of the last number, and it's also like what the length of the remaining strings here, right? So let's say this is 2 here, right? So basically the remaining string is the length of remaining string is also 2. That's why when I check, so first I check if the remaining string is smaller than the current one, right? Then obviously we don't need to check. There's no need for us to check that compare the strings, because all the possible the previous strings will be shorter than this one, right? Then the max L2 will just equal to j, right? Because that's the most we can loop. We can loop for the previous number, right? Else if, right? Else if, and then we need to check, right? We need to check these two numbers. So let's come back to here. So let's say we have j is equal. This is I. This is j, right? So in this case, when the previous string has enough letters, then we need to check if this one is smaller than this one, right? We need to check this too. Then let's write the simple version here. So what is the value for this one? It's going to be the num of what? J minus L to j, right? So this is j, and this is what? This is j minus L, right? If this one is smaller, then the number from j to I plus 1, right? And this one is j to I plus 1. If this one is smaller, then the max L2 will become to L, right? It means that, okay, we can check all the length from 1 to L. So remember, we don't need to go over to L, because whenever this one has like length greater than the current one, it'll definitely be greater than this one, right? Else, right? Else if this check failed, okay, sorry, I need either less or equal. It's going to be a max L2 equals to L minus 1, right? Okay, cool. So that's that. Now we have the max length we need to check for the previous ladder. So all we need to do is that we have L2 in the range of max L2 plus 1, right? So that's why we have to loop through everything from 1 to this. And then we have dp of I, L. Accumulate this one to dp of j minus 1, right? And then L2, right? And then in the end, return what? Return sum of the dp n minus 1, right? So that's our first version, I think. Oh, sorry. That's the dp part, but we haven't handled this no leading zero case, right? where how can we do that? And yeah, let's see. I guess we can just do this, right? Basically, whenever the num of j is equal to 0, right? So basically, if the every time when the start of the current number start with 0, we just do a dp of, it should be dp I l is gonna be equal to 0, right? Well, actually, we already initiate everything to 0, but I'm just trying explicitly write it down here, right? And that's that. And oh, I think we forgot the base case, right? So we have handled everything, right? Except for the base case, because now everything is 0, right? And 0 plus 0 will always be 0. So where would that 1 come from, right? We need a 1, right? Where 1 is the base case. So what is the 1? So 1 is the base case. 1 is when we use the card everything as the card number, right? So no matter how many numbers we have, right? Let's say we have I here, if we use all the numbers as the last number, right? Then that's where we get 1, because this will always one way of doing that, right? So and so to do that, let me see. We can do this, right? So else if, right? Else if j equals to 0, right? So basically, if j is equal to 0, it means that okay, so the last number will be the whole string, right? If that's the case, right? So what do we have? We have dpi and l equals to 1, right? And then I'll have else here, right? So I'll just do this. Okay. And so this is the base case, right? The base case. Okay, cool. I think that's the first version. And let's try to run it. I think this should at least pass. Oh, did I? Is there like, oh, okay. Okay, let's run it. This one will definitely TLE. Let's try it. Yeah, because the reason being is that, yeah, it's timeout, right? Because the time complexity is what? We have a nested for loop here, right? And then we have another for loop here. So which makes this one is like n cube time complexity. And with the constraints 3500, this one will TLE. So which means in order to pass all the test case, we need to somehow bring this one down to n square, right? And how can we do that, right? So obviously this is this is a place where this is the for loop where we want to remove, right? Because these two are kind of necessary, right? But this one, yeah, you know. So how can we remove this one? So as you guys can see, right? So basically, this one is always from 1 to this max length, right? So what does it mean? It means that it's accumulation, right? It's accumulation for dpj minus 1 for dpj minus 1 for all the length from 1 to this max L2, right? So this is going to be it's going to be a prefix, a presum, right? Not prefix. So if we can somehow convert this one into a presum equation, then we can basically remove this one, right? And how can we? Let's try to do it, right? So let's say we don't have this one, and dp I and l. Let's try to define like another presum, right? Presum dp. Okay. For this one, it's going to be the same, right? N plus 1. So this presum dp, right? It's almost the same except for what? Except the total weight that split at ending I, and the length of the last is what? Is from 1 to L, from 1 to L, right? So basically, this one is the it's only the ways for this specific L, but the presum is the ways from everything from 1 to L, and that's exactly what we can use for this one, because that's exactly, like I said, that's the definition of this presum, right? So if we can somehow get this presum, right, and then here instead of for loop, we can just do IL equals to the what? A presum of j minus 1 and what? J minus 1 and oh yeah, and the max L2, right? Max L2, right? So if we can do that, then that'll be perfect, right? Yeah, but this one, but where does this one come from, right? How can we calculate this one here? It means that we need to do what? We need to somehow update this one, right? So how can we update? We need another state transition function for this presum to be able to also accumulate this one, right? And what's gonna be what's gonna that be? So it's gonna be presum of I and L, right? So what is the state transition function for the presum I and L, right? It's gonna be a presum of I L minus 1 plus this dp I and L, right? So remember the definition of the sum, the presum, right? I and L means that is the total ending with I, and the length from 1 to L. Okay, and what does this one mean? It means that all the ways from I to L, from 1 to L minus 1. And what we are getting here, we're getting the total ways that ending with I and the length is specifically L, and that's exactly what is missing from this one to this one, right? Because this one, the presum I L minus 1 plus this dpil will be exactly equal to this one, right? That's how we convert, right? From this one, from the dp version to the presum version, right? So keep in mind that this one has to be outside of the e files, right? Because we need this one to do that, right? And I think that's okay. I think I forgot one more thing. So we have to do a modular, right? Mod equals to in the end. Okay. Right. So that's the change, and now as you guys can see, actually we don't need this dp array anymore, right? Because it will this dp I and L will always be a like intermediate variable, because in the end because all it does, it will just simply use it to update this presum. Oh, and by the way here, and we don't need this presum. We don't need to do a sum here because we already have the presum. It's going to be a presum of what? The last one is going to be n minus 1, right? So ending with this one, and the length is n. So right, so that's the definition of this presum, and that's exactly what we need. So go back to here. So we can just remove this dp for now, because we'll be using this presum all the way, right? We can define it, or we can just remove this one. It doesn't really matter. I mean, I can call this one. Let's call it like current, right? Current is going to be 0, right? We can just do this current, and then current, right? So, right, cool. Yeah, so that's the second version of this problem, and but still, even though this one we have already removed this one, right? But we have this part. See, this slice, I think the worst case scenario, it will also be a O of n time complexity, right? Even though we have already removed this for loop, but we have a slice here. So the last version will be get rid of this part. But let's try to run this one first. Let's try see if this one works. Can give us some better result. What? Wow, I didn't expect this one would pass. Uh, Fine, yeah, because in my I thought this one will give us like another O of n. So this one theoretically speaking, this one is still like n cube time complexity, but for some reason this one passed. But okay, let's try to improve this one. Okay, so what we're doing here is we're trying to compare like two strings, right? Two strings where that each one who is smaller. Okay, basically it could be start from anywhere, right? So this one started from here. So let's say if we compare this, sorry, it has to be the same length, right? It's going to be this one. So let's say the first one start from here, second one start from here, right? So we want to compare these two numbers. So the comparison is fairly straightforward. So we check strings one by one. If the first one is the same, then we move to the second one, and then we move to the third one, and then to the last one, right? And so the moment we see a different letter, that's when we can tell which one is smaller and which one is bigger, right? So and how can we improve this one? We can do some processing such that given like given like this given like this two starting point, if we can immediately know uh, which character we need to compare, right? So for example, if this one is like let's A, B, and C, right? Sorry, this okay. Never mind. I'm using like English letters, but the concepts are the same. So it's A, D, E, right? So if we know if we know the third letter is the first one that we need is the letter that we need to compare, then we don't have to scan from the beginning to here every time, right? And then what can we do about it? So we can do some pre-processing, and we can simply just for each of the two pairs of the string, right? If we can get the longest common string for these two pairs, in this case it's going to be what? So this is I and J. So basically the longest common string of I and J will equal to 2, right? And if we know this one, if for any given pairs, if we know the longest common string, then we know the the next letter will be the one we need to compare, right? Obviously, if the length is the same as the string we're trying to compare, right, and then the or is greater, then they are they're equal to each other, right? So that's why all we need to do is we just need to pre-build this longest common string DP array to get rid of this. And how can we do that? It's easy, right? We simply just use two pointer and to loop through all the strings, right? And then we compare. So this kind of it's a kind of common technique for DP for like two pointer DP problem. So whenever the num I is equal to the num of J, right? So if it's the same, then this the LSI equals to what? LCS I and J equals to 1 plus the LCS of I plus 1 and J plus 1, right? Otherwise, it will simply be 0. Okay, so let's do that. So now we need a third DP array, okay? And this one is what? It's the longest common string. Common string, the length, okay, the length of, okay, length of the longest common string, right? That starts from I and j, right? So for I in range of what? We have n minus 2, minus 1, and minus 1, okay? Because, so the reason I start from n minus 2 is because those two strings cannot be overlapping to each other, right? That's why I start from this one, so that we have the j will always have like position, right? And then for j in the range of what? I plus 1 and n, okay? And the reason I do it from the end is that, in that way, I will be on the left and j will be on the right, right? So that's aligned with our definition. Otherwise, we have to put j on the top and then I below it. It looks a little bit weird, but you can also do it, right? And then if the number of I equal to the num of j, right? And then the LCS of I and j is going to be 1 plus LCS of I plus 1 and j plus 1, right? So basically, if I and j are pointing to here, right? Sorry, this is I and this is j, right? So if these two are the same, then we know, okay, we can simply compare the numbers, the string starting from here to here, right? And yeah, and else LCS of I and j is going to be 0, right? So I think this one there could be a very this one could be more than what we need, because let's say, for example, right, I mean, we have this one, right? Let's say the I is here and the j is here, right? So in our case, like actually in our like below, what we need is that we just need to know if basically we're trying to compare these two, right? If these two are the same, okay, right? But for this one, if everything is the same, let's say this is all AA, right? If they're all the same, right? If this is all A, then the LCS of I and j will equals to what? Will equals to 1, 2, 3, 4, 5. Will equals to 5 instead of 2, right? But five is also fine, because when we use this number, we simply just check if this number is either equal or greater than the length we're trying to compare, right? If it's greater or equal, either equal or greater, then we know this, at least these two numbers, these two like strings will be the same. Okay, right? So it's fine. So it's fine. This one is bigger than what we need. Okay, and there we have that. And finally, we can try to get rid of this part, right? And let me try to comment out this part. So what we have is like this. So we have else, right? So I'm going to like this common length. I call it CL, the common length, right? Common length of the LCS from what? So we have two start. The first one is j minus l. The second one is j, right? So that's the number. That's the value we pre-processed. And what we do, we compare. So if the CL is either equal or greater than L, so this one means that, okay, the two strings are the same, right? Or the num of, so if the CL, when the CL is smaller than L, then it means that, okay, so these two strings, right? So we have, because we know the length we're comparing is like it's L, right? So this is the I and this is j. So when this one fails, right? So when this one fails, it means that these two strings are not equal. Then the number we're trying to compare is what? So let's say that the CL is equal to 2, right? Then it means that these two numbers are the numbers we're trying to compare, right? Or the number of what? It's going to be a j minus l plus CL. Okay, right? So because that's a start, right? That this is I, and I plus CL will be this one. And if this one is smaller, then the num of the other one. The other one is j, right? J plus CL, right? So we can simply just navigate to the numbers we're trying to compare directly without looping through. That's the benefit of processing this LCS, right? And if these are the two reasons, then we do the same, right? We do this. And then we know, okay, we can use it. We can use this length. Otherwise, same thing, right? Otherwise, max this one. Same for this one. Okay, I think that's all we need to do here, right? So let's try to run this one last time. Memory, what? What memory limit exceeded? Wow, I'm not expecting that. Is it because I did this? Okay, let me see. Oh, interesting. Okay, seems like we cannot even pre-allocate too many spaces either. But for some reason, the last version didn't improve our runtime. For some reason, I think it's because the online judge is not that accurate. But for sure, as you guys can see, the last version. Oh yeah, so this time it's faster, right? But as you guys can see, for sure, for the last version, this one is n square, right? And here we also have n square, right? Time complexity, because everything here is like O of 1, right? This is O of 1, and this is also O of 1. So the last version is definitely n square time complexity. And that's it, right? I think that's everything for this problem. Okay, so I mean, the idea, at least for the first version, shouldn't be that hard to come up with, right? So what makes this one a real hard one is how can we improve that, especially for we have two challenge here. The first one is that how can we get rid of this for loop here, right? So what we did was instead of using the first version of DP, we converted it into a Presum, right? Where I think this is a common technique. Whenever you see like this accumulation from one to this one, I think we can most likely get rid of this for loop by introducing another like Presum DP array, right? And then the second one is this one. So this one is a little bit tricky, I would say that. So how can we get rid of this one? So we just simply pre-process all the longest common strings for each of the pairs, right? And yeah, there you go. I hope you guys like this one. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.